So as we have said, if you see, let's clean the slide once more. And if you see, we say this is the initial state, okay? And this is a final state. So every input that you have should start from the initial state and complete its phase at the final state. So if it is anywhere in between, then it's not going to be acceptable. So let's take the first word that we have taken earlier. Let's have the annotator. So if you have the word talk, okay, if this is a word, as you can see, how many inputs do we have? The word talk has 4 letters. So it tells you that the word should start with T. So as you can see, let's change the color to make it more clear. As you can see, the word T, just a moment. As you can see, it starts with the word T, so it's acceptable. After T, what do we have? It has the letter A, so it's acceptable. After A, it goes to L. It's also acceptable because that's the input that we have. After L, it has K, and as you can see, it has K. But after K, what do we have? We have nothing, which tells you that after K, your model should arrive at the final state. And from the 4 passes that we have in here, the one that has no additional string at the end is the first one, which says there is no additional thing, which means this is empty malatum. So in this case, it says the word is in its base form malatum. When we say it is in a base form, it means it doesn't have any other morphological elements into it. Now, what if we have another word? Okay, let's have another word. Let's have words like, let's say, let's say, caring, a mill word ይኖራል. Okay, in this case, it tells you that the input word starts with key, C, right? But the finite state model said that a word should start either with T or with W. So it means that this word is not acceptable in this language. So by using such kind of a finite state model, you can check a spelling of a word. You can check whether the word is correctly constructed or not. Now let's have another example again here. Let's have a word, let's have the word, for instance, worked. Okay, let's have the word worked, just for the purpose of tagging them or linking them with the finite state model. Let's give a space to it. Okay, now it says the input, mind you, don't forget what we have said earlier. We said in a finite state model, we have a state, a transition, and an input. The input is something that's given by the user. And the states are, where there would be an exchange between the input and the output. And the transition is moving from one state to the other. So in this case, we have the initial state, the final state, it is part of a state. We have many other states, and we have a transition. You see, the circles are the states, and the arcs are the transition. So what we are going to do in here is check if the input, this is the input string, check if the input string is understandable or something that you can analyze using the finite state. So it says it starts with W, and it goes in line with the finite state model because it starts with W. Then after W, you have 2 options. Either you can have A or O. So as you can see in the input, it has the letter O. After O, it has the letter R. After R, it has the letter K. Mind you, we are trying to check the input against the finite state model. Then after K, what do we have? We have 3 options. And as you can see, the first option says it should end here. There is nothing after K. The second one says after K, I should have S. The third one says after S, after K, I should have I. And the fourth one says after K, I have E. So as you can see from the 4 options, the one that's chosen is the 4th one. Then after E, what do you have? After E. So E is taken. After E, we have D. So as it shows you in here, after E, I have D. Then after D, what do you have? It goes to the final state. And it shows you that the word W-O-R-K-E-D is in a past tense form. So in each of the transition, you can have a linguistic information or you can have any other string. In another formats, they put it in such a way. For instance, there are different kind of modeling for a finite state model. Sometimes they put it in such a way. እዚህ ላይ ለምሳሌ ምን ይላሉ? ቲ ኢንፑት ሲሰጠኝ መልሼ ቲ ይሰጠዋለሁ ይላሉ። ኤ ሲሰጠኝ መልሼ ኤ ይሰጠዋለሁ። ኦኬ አር ሲሰጠኝ መልሼ አር ሰጠዋለሁ ብሎ ሞዴል ያደርጉታል። እዚህ ጋር ስንመጣስ ምን ይላል? ምንም ነገር ከሌለ ቤዝ ፎርም ነው እለዋለሁ። If it has S at the end, I will say this third person singular. Mind you, this means third person singular ማለት ነው. It's a representation type. In this case, if it has I, N, G, I will say this is in a progressive form. If it has E and D, I will say it is in a past tense form. So this is how, mind you, we said in NLP, it's about representation of knowledge. Now in here, we are representing morphological knowledge in a finite state model. Is the point clear? Is it clear, Sakatar?
Yeah.
Okay. Now, what if the input word is this one? What if the input word is, let's say, እንደዚህ ቢሆንስ?
This model it's not existent in this model.
ምን ይሆናል?
Because
okay, proceed.
From initial point ይሄድና እዚህ ኬጋ ከደረሰ በኋላ እንትን የለውም
እስከ ኢ ድረስ ይደርሳል። እንደዚህ ይመጣል። ቲ ኤ ኤል ኬ ኢ ይመጣና ከኢ በኋላ ምን ይላል? Your finite state model is expecting D.
Yeah.
But your input has R. ስለዚህ ምን እንላለን? This word is not a correct English word because it's not covered by this rule ማለት ነው.
Yeah.
Is the point clear, David?
Yes.
David? Is it clear?
Yeah.
Okay, what about undo? Undo. Undo.
Yes, sir.
Is the issue clear?
Also, yes, sir, I'm clear.
Okay, good. Now, if you have this, now how many possible words can you generate from this finite state model?
From this finite state model.
How many words can you generate?
3.
Okay, give me the 3 words.
Talk, walk, and work.
Is that all?
Talk.
Eh?
Walk.
Okay.
Yeah.
Lelas.
Yeah.
Lelas. What else do we have? Talking. Adam? Lelas.
Yeah.
Lelas.
Working.
Lelas.
Working.
Lelas. Sorry. Eh.
Working.
Okay.
Working.
Walk it out. No, walked no. Okay. Walks. Rasachuacho.
Yeah.
Works. Talks. Talked. Okay. Sorry. Arala? So how many words do we have?
12.
12. But one thing that they have in common is this one. Let's say, for instance, let's put them in such an order. Okay. if we put it in such order, as you can see, each of them, either they start with W or they start with T. If they start with T, each of them, they are followed by A. If they are followed by A, then they are followed by L. If they are followed by L, they are followed by K. ከዛ በኋላ either they end with ED, S, or ING ማለት ነው. The other, as you can see, you can have words that can start with, let's delete this one, that start with W, but the W has two options. If it starts with W, either it can be followed by O, or it can be followed by A. And you can see it from the finite state model. You see, after you have W, it can be followed by A or O. So as you can see, after W, you have two options. Either it is O or A. Then after that, if it is followed by O, then the only option that you have is, then it will be followed by R, then followed by K. If it ends with, or if it goes to the direction of A, then it will be followed by L, then finally it is going to be followed by K. So mind you, this small finite state model can give you all these possible words. Now the question is, what if you are supposed to develop a finite state model for all the English words? What do you need, for instance, if you have to develop a finite state model for all the English words?
It should have to include the exceptional case and the
all
ER
possibilities. Yeah, all possibilities, right?
Yeah.
Which means
Yeah.
you have to go to the dictionary and see the starting symbol of every word. ስለዚህ አሁን እዚህ ላይ በቲ እና በደብሊው ብቻ ነበር አይደል ያለው? ኦኬ። ስለዚህ ምን እናደርጋለን ማለት ነው? በሌላ የሚጀምር ካለ እዚህ ጋር we are going to create another path ምን ብለን with the word K. ሌላ ካለ ደግሞ እዚህ ጋር እንጨምራለን with the word, let's say, S. እዚህ ጋር ካለ ደግሞ እንጨምራለን with the word W አለን F, for example. So when you do that, ምን ይሆናል? The finite state model is going to be very big. Now, even if you want to do it for Afan Oromo, for Walaita, for Tigrinya, for any other language, then you have to think about, you need to have all the knowledge of how words are formed, of how characters are going to be followed one another, or how they are going to be sequenced. And this is what we call is a finite state model as one type of approach for natural language processing application development. Okay, now let's do further analysis on this one. Okay, let's do further analysis on this one. So as we said, we can use a finite state model. Don't forget this one. We said a finite state transducer can be used to generate a language. Generate means produce a word, or it can also be used to analyze a language, which means understand a word that's already written. So in this case, let's see how it is used for the purpose of generation. Okay. Let's see how it is going to be used for the purpose of generation. So if I give you the word work, okay, if I give you the word work, and if I ask you to make it third person singular, what do you do? Mind you, we are going to follow the same step. W, as you can see, will be linked with W, O would be linked with O, R would be linked with R, K would be linked with K, because it means whenever I give you W, you'll give me W. Whenever I give you O, the output will be O. Mind you, this means the input output ማለት ነው. If I give you this, you have to give me this, or if I give you this, you can give me this ማለት ነው. It is, we say the finite state model can be used in two directions, right? For analysis and generation, which means you can change the input and output ማለት ነው. You can interchange, or whenever the input is given, you can give me the output. Whenever the output is given to you, then you can give me the expected input for that one. So ይሄን ካደረገን በኋላ ምን ላይ ደረስን? It says, I'm going to give you third person singular. So from these four options, you have to choose third person singular. So if you want to make it third person singular, ምን አለ? Attach S to it አለ. So instead of third person singularን በምን ተካው ማለት ነው? With the value of S. And it says the word is going to be works. So what does it mean? Literally, if you are going to, if you have to write it, በጽሁፍ ብናስቀምጠው, this means this means what is the third person form of the word work ማለት ነው። This is a question that we are asking. You see, the question is, what is the third person singular form of the word works? Because you said works ካለ በኋላ plus third person singular አለ ማለት give me the third person singular of the word work. and ሞዴላችን ምን ይላል? w ወሰደ on ወሰደ r ኬን ወሰደና ልክ መጨረሻ ላይ ምን አለ? third person singularን እዚህ ውስጥ ይፈልጋል። ካገኘው it gives you the output yes and it will say this is works. What if you have such kind of an input? እንደዚህ ቢሆንስ? works below, no work below. Let's say give me the noun form. እንደዚህ ብለውስ? እንደዚህ ብለው what's going to happen? Martha.
Yes, doctor.
What's going to happen if I say work plus noun below?
So I think first person singular.
No. ይሄንን ነው የሰጠሁት ማርታ። work ብዬ noun አልኩት instead of third person singular.
ቤዝን ነው የሚወስደው።
ለምን ይወስደዋል? ቤዝ የሚል የለሽም እኮ እዚህ ጋር።
Okay.
So this will give you no output.
Okay.
Because your finite state model doesn't represent any noun. There is no knowledge about a noun ማለት ነው። But ይሄ እንዳለ ይቀመጥና what if I add this one? እንደዚህ ባስቀምጠውስ? እዚህ ጋር አንድ ስቴት ልጨምርና ኦኬ እዚህ ጋር አንድ ስቴት ልጨምርና እዚህ ጋር የሚመጣ እንደዚህ አይነት ጽሁፍ ቢኖረኝስ? እዚህ ጋር አስቀምጥና ፕላስ ናውን ሲሆን ኢአር አስገባ ብለውስ? አሁን እንዴት ይሆናል? if I say work plus noun ብለው ምን ያደርገዋል ማለት ነው? the output is going to be
Worker.
አያችሁ worker ሆነ ማለት ነው። to give it a property of a noun we are going to add er to it ማለት ነው። አያችሁ you can increase or you can expand your finite state model to cover more things, but it all depends on the knowledge that you have on how to make it progressive, how to make it past tense, how to make it a noun, how to make it an adjective or anything that you have ማለት ነው። Okay, did you get the point?
Yes.
All of you? Okay. So if you don't have any question, then let's move on to the next step on the same type of model. So this is for generation. As you can see, it generates a word. What if I ask you to analyze? Analyze means I'll give you the word and I want you to tell me the property that it has. So if I give you the word talked, what do? The process is the same. The input is T, then as you can see, the output is going to be T. The next input is A, then the output is also A. The next input is L, then the output is L. The next word is K, letter is K, then the output is K. After K, what do you have? The input is E. So from the 4 options that I have, I'm going to look for the input which has E. In the first case, the input is empty. In the second case, the input should be S. In the third case, the input should be I. In the fourth case, the input should be E. So as you can see, instead of the top 3, I'm going to take the the fourth path. So it is E. After E, what do I have? I have D. So I will say this word is in a past tense form. Mind you, whenever you give me the word talked, I would say it is in a past tense form because I know that it is based on the finite state model. Output T, A, L, K ሰጠኝ, which is talk. That's why የሰጠኝ output ምንድን ነው? Past ይላል. So I would say talk is in a past tense form ብዬ እነግራለሁ ማለት ነው። So as we said, a finite state model can be used for analysis at the same time generation. So this diagram is descriptive of this path. If you give me talk and pass, I'll say talked. If you give me talked, I'll say talk and passed. So as we said, it can be used in a bidirectional manner. You can use it for analysis. You can also use it for generation. And this is what we mean by a finite state model. Now, this is going to be your quiz. What you are going to do is, as you can see, this is a start symbol. It explains it. S1 is a starting symbol, and S4 is the ending state. S1 is a start, and S4 is the ending state. Now, from these, try to generate 8 possible sequences. And what you're going to do is post those 8 possible sequences on our Telegram group after this class. Okay? Did you get the point? This is your assignment for today. This is a finite state model. S1 is a starting symbol, and S4 is the ending state. The start symbol and the end symbol. And from this finite state model, generate 8 possible sequence of characters. 8 possible sequence of characters from this finite state model. Okay. Now, moving on, the next type of approach that we use in natural language processing after a finite state model is formal rule systems. Formal rule systems are the one that tries to represent the rules that we have in a linguistics construct. For example, as we have seen earlier, if you think about grammar, grammar is governed by the rule of the language. If you think about regular relations, if you think about context-free grammar, they are all concerned about rules in the language. For instance, for the English language, we say, whenever you have a determinant, then it will be followed by either an adjective or a noun. So this is a rule. Okay, whenever you have a determinant, it can be followed by either an adjective or a noun, because you can say the villain, you can say smart, big boy. So as you can see, after a determinant, I have an adjective. Or I can even say smart boy, which tells you that, sorry, after a determinant, I can have a noun, or after a determinant, I can have an adjective. Now, from where do we get these rules? It's not a machine generated. It's not done by a computational system. It is a formal rule that we have in the language. So we know that formal rules are one approach for natural language processing. So regular grammars, regular relations, context-free grammar are very important formal rules that we have. And most of the time, finite state machine and formal rule systems are going to be used, especially to represent phonology and morphology. And that's what we have done earlier also, right? When we see the word generation, if you see this finite state model, what does it do? It tells you a morphology of the English language for a few words. It tells you how letters are combined to create the base form, to create the third person singular, to create the progressive form, to create the past tense of a word, okay? Just like that, the formal rule systems, at the same time, a finite state model are used for the purpose of phonology and morphology, and also syntax, because syntax is concerned about word orders. It's concerned about word grouping. And that is talking about grammar. Grammar is about word order, right? It checks whether 2 words are supposed to appear in that sequence. And what you do in the formal rule systems, as well as in a finite state model, is you do searching. You search over a space. If you recall this diagram, what did we do? To identify whether a word is a valid or not, to generate a word based on the grammatical feature, what we have done is we have searched over this network. We go through the network, and that's searching. So that's why we say that in a finite state model or in a formal rule system, we deal with searching through the space. In this case, we search through the space of the states to represent or to, to associate the input with the output. And since searching is one of the costly computational tasks that we do, most of the time people use dynamic programming and different kind of search methods like the A*, the best first, or the depth first searching method to arrive at the solution very fast. Mind you, in NLP, we do many searching tasks, and making the search process to be efficient is a most important element. The third approach that we have in NLP is logic. So logic is concerned about capturing a relationship between elements. Some elements should be related with one another. Some elements should not be related, even though they belong to the same group, even though they belong to the same class. Maybe they might not be used in conjunction with other elements in the other group. So logic is concerned about how, semantic relationship can be created, how dependencies can be represented, how feature structures should be represented. So these logical representation have traditionally been used for the purpose of semantics, pragmatics, and discourse. If you remember, we had one example to illustrate semantic anomaly. We can say the table ate the apple. If you have this one, we know that we could have said the boy ate the apple. And we said the second one is correct. But mind you, if you see the part of speech for each of them, this is a determinant, okay? Then we have a noun, then we have a verb, then we have a determinant, then we have a noun. For both sentences, the structure is the same. Determinant followed by a noun, followed by a verb, followed by a determinant, followed by a noun. And this is allowed in the language. But the only problem that we have in here is, while boy is an object that can perform the action of eating, table, contrary to that, cannot perform this action. And the relationship between table and the action of eating can only be expressed through knowledge of logical relationship. That's why we say this sentence has a semantic anomaly ብለን ያስቀመጥነው ለዛ ነው. It has a semantic anomaly, and the anomaly is because due to the fact that table is not an object that can perform the action of eating. So that's why we say when it comes to semantic, pragmatic, and discourse, we are going to dwell more on the approach that are developed through logic or logical representation. So please pay attention to these different categories of method that we have. When it comes to grammar, when it comes to syntax, when it comes to morphology, we use finite state model and formal rule systems, because this type of knowledge or knowledge of a language, like when it comes to phonology, morphology, and syntax, they are more governed by formal rules and transition from one sequence to the other. Whereas when it comes to semantics, pragmatics, and discourse, we dwell more on logic, which shows some kind of dependency, some kind of relationship between constructs of the language. The fourth one is probability, and probability is a kind of a cross-cutting approach that we have in NLP, because probability is going to be used whenever we have some sort of uncertainty. Whenever there is uncertainty, then you are going to look for a statistics that gives you some level of confidence to make a decision. So whether it is a finite state model, whether it's a formal rule system, or even a logic, it can be, supplemented with a probabilistic model. So a probabilistic model will do counting, and that counting will help the system to decide whether, it will help to decide whether, to side with one of the options that are available. So whenever you have uncertainty, or whenever you have some sort of ambiguity means you'll be challenged to make a decision, then probability can be used. For instance, you are going to have n possible choices, okay? And that n possible choices might be ambiguous to make a decision. So what we are going to do is choose the most probable one. For instance, if you see the word book, it can be noun sometimes, it can also be a verb. Now the decision is which one is the most probable choice in a specific case. So you can say, for instance, in a corpus or in a collection, if you have the word book, okay, if you have the word book, let's say 500 times, and from these 500 times, let's say if 100 of the time, if it's used as a verb, and 400 of those times, if it is used as a noun, then most probably you'll say it is a noun. And you are going to be 400 over 500% accurate in this decision, because from the 500 instances, we know that 400 of those times it is a noun. So if you say noun, if say it's a noun, then you are going to have this percent of being correct, 4/5 mallet, which is 80% of the time you're going to be accurate mallet in this case. Okay, so this is a kind of knowledge that you can add using a probabilistic approach. So another major advantage of a probabilistic model is it is the one that we use in a machine learning approach. Machine learning, most of the machine learning algorithms that we have, they use a probabilistic approach to make a decision. So as we said earlier, machine learning is the state of the art that we have these days. So whether to develop the rule for finite state automata, or for a rules-based system, or for knowledge-based searching, or for classification, we use different kind of machine learning approach, which are said to be very, very powerful. And most of the time, people use a machine learning approach rather than this. Now, saying this much about the approach that we have, let's spend only a few minutes on the idea of intelligence, okay? Now, whenever you develop an NLP application, we know that we are trying to make the machine to be intelligent. And how do you judge whether a machine is intelligent or not? So in this case, the use of a language is one type of, classifying machine to be intelligent, because the use of a language requires thought and understanding. Okay, the machine should think, and the machine should understand what the human beings are saying. And for this purpose, we have in 1950, we have the Alan Turing, which is the Turing test. The Turing test, the purpose that we have in here is to judge whether a machine can be, classified as intelligent or not. So it is an experimental, an empirical study. So what it does is the objective is how to measure intelligence of the machine. So in 1950, Alan Turing came up with, an approach which says, if a machine can be accepted to be intelligent, or a machine can be accepted to be intelligent, if it can actually fool a person or a judge that it is actually conversing with another human being. Like whenever you type something to the computer, and if the computer replies to you, and if you say, this is a human being, then we have to actually judge it as intelligent. Like whenever a speech comes out of the computer, if you assume that it is a real human being talking to you, then it means the machine is intelligent. So even though the concept was, or the hypothesis was built in 1950, in 1966, an application was developed. The LISA application was developed for this purpose. And this application, based on the Turing test, what it does is it pretends to be a psychiatrist. Mind you, this is a machine. This is a computer program. It pretends to be a psychiatrist, and it tries to converse or make a conversation with a patient using teletyping or the keyboard type. So what the machine does is, based on whatever word that you type, from those words, it takes a keyword to identify some kind of pattern. And based on that pattern, it gives you a response, okay, based on the keyword that you type. So we are going to see one very simple example. So the Turing test is this one. There is a human being here. And for the questions that this evaluator raises, the computer can give an answer, and the human being can also give an answer from the other side. And if this person cannot, make a distinction between these two replies, between the computer and the human, then you can say the computer is intelligent, if the evaluator cannot distinguish one over the other. So this is the example that we have. The LISA program in the 1960s, as we said earlier, it tries to converse with a person. So for example, the system, if you see the interaction, the system says, is something troubling you? Mind you, it starts with a question. And the person, a real human being, says, men are all alike. Now, from these inputs, the machine will generate the next question. It says, what is a connection, do you suppose? Mind you, because it says it has the word alike, alike is about comparison. Okay, so from this keyword, it generates the next question. So what is a connection? Then the person says, they are always bugging us about something or other. So in this case, it was difficult to identify a keyword. So it says, can you think of a specific example? Since the machine was not able to extract any additional question from the response, it gives you some general question so that you give the machine a leading keyword. Then it says, well, my boyfriend made me come here. So in this case, then from this one, it can come up with another question. It says, is it important to you that your boyfriend made you, to come here? Mind you, it picks some of the keyword from the response. And from that one, it generates the next one. It says, I'm depressed much of the time. In this case, then there is a keyword for a psychiatrist, right? Whenever a person is depressed, then it means there is a question to be asked. I'm sorry to hear that you are depressed. Then it's true, I'm unhappy. Can you explain what you mean by unhappy? You see, in each of the questions, it derives some keyword from the response from the human being. Now, in this conversation, if the human being who is conversing with the machine think that this is a psychiatrist talking to him, then it means the legal system is intelligent because it fooled the patient malady as being a person. So this is how people used to test whether a machine is intelligent or not. But these days we have more sophisticated testing mechanism, like if it can generate an intelligent speech, if it can generate a word, if it can do summarization, if it can do translation from one language to the other, then why not we say the machine is intelligent? So saying this much, there are many NLP applications that we have, like question answering, text categorization and text routing or email routing, text mining, extracting new knowledge from an already existing text, machine assisted translation, language teaching and learning, spelling correction, grammar correction, text to speech system or speech recognition, natural language dialogue, which means a speech conversation, information retrieval, extraction, document classification, image analysis, automatic text summarization, spelling and grammar, text proofing or checking and correction, machine translation, which means a complete machine translation, a story understanding from a movie, plagiarism detection, and many other applications are available these days. So if you go, Google it, then there are many NLP applications for many, language that we have in the world that depends on analysis of language construct or language data elements. But the challenge that we have in here is language is a collection of words, rules, and exceptions. Wherever you go, it is words, rules, and exception. And we have ambiguity at all levels, at a word level, at a rule level, at exceptions level, at phonology, morphology, syntax, semantics, pragmatics, at all level we have ambiguities. And there are many different languages all over the world, and still it's a big challenge. And language has some cultural elements, even like Amharic that's spoken in Addis and in other parts of the country are quite different. And the language are, they are not equivalent in how they express, but everything is expressed. Like a single word in Amharic can be interpreted with 5 words in English, which means the way they, express things is not equivalent. They are systematic, they keep changing. The sources are from different parts. So even though language is very obvious for us, it is a big deal for a computer system. So this is what we have in the first chapter. Please go through these project ideas to understand how you're going to do the project. So this will be the end of the first topic. Tomorrow we are going to start the second topic, which is morphology. Okay.